the Euler-Lagrange equations from this sort of formalism? Who's not familiar with that? Okay, 2 or 3. Okay, well, let's quickly sketch what you do. Okay, so we get the classical path, so let's call it Q classical of t. From this, and something, so we call an extremal. So, if you don't know what that means, it's just, if you think of an ordinary function, f of x, then you can look for turning points. So this is specific values of x where the derivative of the function vanishes. So this action here, it's not exactly a function, it's what's called a functional, because it doesn't just depend on a given finite number of variables, it depends on a whole path. So this means you choose the whole path q of t, and then you put it in here, and you do this integral, and you get some number. So extremal is just very much like a turning point, and, well, so of this functional S of Q. Okay, but remember this Q here, I'll usually drop the Q of T, but it means the whole path. It's not just a single point. This is the whole path you choose and put it in there and evaluate that. So opposed to the Lagrangian itself, at a given value of time is just a function that depends on Q and the velocity Q dot. But the action, because you have to integrate over all values of T, depends on the complete path. Okay, so how do we do that? Well, it's just very much like what you do for functions. One way to get the turning points, basically you expand it as a Taylor series and ask for the linear order term in your expansion to vanish. So what we have So we take some path q of t and add some little variation onto that, eta of t. Okay, so you imagine okay, so take some path like that, and then you add little bit onto it. So small variation goes maybe along a similar path, but not quite. Okay, so this red one would be q plus eta. Okay, so you put that into Lagrangian, so it's just a function. So this we can expand, so it's L of q dot. And then you just expand using Taylor series, so you get dl, chalk keeps breaking, dl dq times eta plus dl dq dot, eta dot, and then terms of order eta squared. And, well, I mean by that eta squared, eta dot squared, and everything like that. Okay, so this is what we get to linear order, and then what we have to do for the action, we have to, of course, integrate. So the action at q plus eta, so we integrate this thing over time. So obviously when I put an integral over time on the first term, I just get the same as what I would have for the action evaluated for the path q. So if I ignore all of this stuff, then the integral of that over time is just the action for the path q. And then I have to integrate this here, integral over time of, let's take these terms together, dl dq times eta plus dl dq dot eta dot, and then again just plus order eta squared. So of course I've not defined exactly what I mean by small eta, but basically it's somehow the path q plus eta should be very close to the path q, and also the derivatives should be very close. Okay, so this is just like a Taylor expansion for a function. You take it at some q plus some small variation. It's the value of the function, and then you get a linear term. So this has got eta dot here, and then higher order terms. So the turning point of a function, of course, is when this linear order term vanishes. So that's equivalent for a function. That's just being the derivative vanishing. Now we can find the condition for that. Let me not write it all again. So we want this term to vanish here for the classical path. So that's just what I say. The classical path is the one that corresponds to the turning point, and so this thing should vanish. And, well, it's not just for one specific value. If you think of a function several dimensions, you should be able to move in any direction at all, and the derivative should vanish. So this eta, or variation, should be somehow arbitrary. So with arbitrary eta of t, and let's be precise if I bring this back, the path q plus eta should satisfy the same conditions as the path q, the same boundary conditions, which should start at qi and finish at qf. So obviously this means if q does that, then q plus eta will only do that if this function eta of t vanishes at time 0 and at time capital T. So you add on this path, but you keep the condition that the endpoints stay the same. So what we're doing here, we're not varying the endpoints. So other than that condition, it's just something arbitrary. But that keeps our endpoints the same. Okay, so how do we do that? Well, the way to do that, we can use integration by parts on this second term to take the derivative off the eta. So this thing here. Okay, so the first term, we don't do anything with it, we just leave it as it is. The second term, integration by parts, what you do is you take a derivative off, you've got a product of functions, you take a derivative off one of them, put it onto the other one with a minus sign. And you get also some boundary terms, but because eta vanishes at the endpoints of your integral, so the integral, if I've been precise, should be from t equals 0 to t equals capital T. Because eta vanishes there, these boundary terms don't contribute. So when you do that, you get integral dt dl dq minus dl dq dot, minus d by dt of that times eta. Okay, so it's just the second term. We've taken the derivative off the eta, this dot d by dt, put it onto the other term with a minus sign. And that's us. So basically, this integral, eta then, apart from the conditions that it vanishes at the endpoints, there's no precise form for that, so we're allowed to take arbitrary etas that satisfy that. And so the only way this thing will be 0 will be, of course, if this bit in here is 0. So if I can vary eta as I want, then the integral will always give me, I'll always be able to choose some eta so that this integral gives me a non-zero value, unless this bit in here vanishes. So this Okay, so that's, and this is the Euler-Lagrange equation. Okay, so that's how we get classical mechanics starting from the idea of integrating Lagrangian, forming the action, and we look for turning points. Now, of course, you'll say, well, why did I do that? It seems rather an arbitrary procedure. And of course, the idea is simply that that's one way you can do it, and you can see if you put in the Lagrangians we've been talking about, you get the usual equations of motion that you would get from the Hamiltonian or from Newton's laws or whatever. So that's just a method you can use, and it works. So what the quantum mechanics path integral actually is links in quite nicely. This idea of summing over all the paths, we'll see automatically reproduces this idea here that the classical path, which we imagine the most likely path to take, is given by the condition that this equation is satisfied, or more basically, is given by the condition that for the classical, if I take Q to be the classical path, and I expand to consider paths near the classical path, so Q plus eta, like this red one up here, that the action is given by the action for the classical one, and then the next term vanishes. So it's the next term of linear order in eta vanishing, that's the condition that we'll see goes from this quantum thing here with sum over all paths to reproducing the classical one, where we have a specific path. Okay, so how do we do that? So basically, if you take a path Q of t, then what does it contribute to this path integral? You work out what the action is, put it in there, and that's this factor here. So it's e to the I times some real number, so it's some phase, and that's the contribution you get from that path. Now we'll look at some nearby path, like this Q plus eta here. So well, it just contributes then to the same form, e to the I over h bar, and the action then evaluated for the path Q plus eta. And now what we want to do is compare, if we add these, think of adding these two things together, how do they add together? So the point is, of course, this exponential of I, so we've got the action over h bar. So the action over h bar is the phase. So if you think in the complex plane, you're going round the unit circle, and you go round by an angle s over h bar. And if you add up numbers like that, well, of course, It's just exactly what we were talking about with the interference with light. They can add up in phase, so if these phases are the same, then they add together. If the